Episode 13 Specialty Functional Pigments, IR Reflection, Conductive and Anti-Corrosion in Automotive Coatings. In this episode, we explore specialty functional pigments, which go beyond traditional color contributions and provide unique optical, thermal, and protective properties in automotive coatings. While conventional pigments primarily influence color, opacity, and gloss, functional pigments are engineered to impart specific performance benefits such as infrared, IR, reflection for heat management, electrical conductivity, anti-corrosion protection, and other advanced functionalities. Understanding these pigments is essential for designing modern high-performance automotive coatings that meet aesthetic and functional demands. Infrared reflective pigments are designed to reflect a portion of solar radiation, particularly in the near-infrared spectrum, which can constitute up to 50% of the energy from sunlight. By reflecting IR radiation, these pigments reduce surface heating of the vehicle body, contributing to lower cabin temperatures and reducing air conditioning energy consumption. This property is especially valuable in dark-colored coatings, which typically absorb more heat than lighter colors. Infrared reflective pigments include specially coated titanium dioxide, ceramic pigments, and metal oxide-based formulations engineered to maintain visible color, while selectively reflecting IR wavelengths. The effectiveness of IR reflective pigments depends on particle size, composition, and coating technology. For instance, core shell ceramic pigments are designed to optimize the refractive index contrast, enabling reflection of IR radiation without significantly altering visible color. Particle morphology, surface treatment, and distribution within the binder system are carefully controlled to balance heat reflectivity with gloss, hiding, and application properties. These pigments must also maintain durability under UV exposure, thermal cycling, and environmental stresses. Conductive pigments impart electrical conductivity to coatings. They are commonly used in applications requiring electrostatic discharge, ESD, protection, electromagnetic interference, EMI, shielding, or anti-static properties in vehicles. Conductive pigments often consist of carbon-based materials, such as graphite, carbon black, or carbon nanotubes, or metal-based powders, such as silver, copper, or aluminum flakes. The conductivity depends on particle concentration, aspect ratio, connectivity between conductive pathways, and dispersion quality. Too low a concentration results in insufficient conductivity, while excessive loading may negatively impact gloss, color, and rheology. Achieving uniform dispersion and orientation of conductive pigments is essential to ensure consistent electrical performance without compromising visual appearance. Anti-corrosion pigments are a critical class of functional pigments, primarily used in primers, fillers, and base coats to protect metal substrates from rust and environmental degradation. These pigments include zinc phosphate, strontium chromate, less used due to environmental regulations, calcium phosphate, and various proprietary conversion-treated pigments. Anti-corrosion pigments function through chemical passivation of the metal surface, sacrificial protection, cathodic inhibition, or barrier formation to reduce moisture and oxygen penetration. Their effectiveness depends on pigment particle size, surface treatment, concentration, and dispersion within the binder matrix. Proper incorporation ensures long-term corrosion resistance, while maintaining smoothness, gloss, and compatibility with subsequent coating layers. Functional pigments also influence rheology, mechanical properties, and application behavior. Plate-like or high aspect ratio functional pigments can increase viscosity, thixotropy, and sag resistance. Particle interactions with binder polymers, extenders, and other pigments must be considered to avoid flocculation, surface defects, or settling. For example, the addition of conductive carbon pigments requires balancing dispersion energy and dispersant selection to prevent aggregation, which could reduce conductivity and visual uniformity. Similarly, IR reflective ceramic pigments may require controlled milling to achieve optimal particle size for both reflection and hiding power. The integration of functional pigments into multi-layer automotive systems requires careful design. Primers may contain anti-corrosion pigments, while top coats incorporate IR reflective pigments or conductive layers. Clear coats and sealers must maintain compatibility with functional pigments to prevent migration, discoloration, or loss of effect over time. Surface treatments, particle coatings, and binder selection are key to ensuring pigment stability under curing, environmental exposure, and mechanical stress. Durability is an important consideration for functional pigments. IR-reflective pigments must resist photodegradation, thermal expansion, and mechanical stress, while maintaining consistent reflection properties. Conductive pigments must maintain network connectivity over time, despite mechanical stress, vibration, and thermal cycling. Anti-corrosion pigments must remain effective in the presence of moisture, salts, acids, and environmental contaminants. Accelerated weathering, thermal cycling, and corrosion testing are used to validate performance during formulation development. In addition to performance, regulatory and environmental considerations influence functional pigment selection. Some traditional anti-corrosion pigments, such as chromates, are restricted due to toxicity. Modern formulations often rely on phosphate-based or other environmentally friendly alternatives, while achieving equivalent protective properties. Similarly, the particle size and surface coatings of IR-reflective and conductive pigments must comply with safety, handling, and environmental regulations. Functional pigments often have synergistic effects with other pigments and additives. For example, IR-reflective pigments can be combined with effect pigments to maintain visual aesthetics while providing heat management. Conductive pigments can coexist with colorants, provided dispersion and binder compatibility are managed to maintain both electrical performance and color consistency. Anti-corrosion pigments and primers can enhance adhesion and durability for topcoat layers containing effect or organic pigments. In summary, specialty functional pigments expand the capabilities of automotive coatings beyond mere color. IR-reflective pigments contribute to thermal management, conductive pigments provide electrical and EMI protection, and anti-corrosion pigments protect metal substrates from environmental degradation. Their performance depends on particle composition, morphology, surface treatment, concentration, dispersion, and interaction with the binder and other pigments. Mastery of functional pigment selection and integration is essential for creating automotive coatings that meet both aesthetic and advanced performance requirements. If you have any doubts about IR-reflective, conductive, or anti-corrosion pigments, their selection or integration into automotive coatings, leave your questions in the comments and I will clarify them in detail.